Okay, right here we have an exponential equation. We do have the basis of 7, and this power here is x plus 5, the power here is 8. Now, if you're solving an exponential equation with no logs, you have common bases. So, if you have common bases, you can cross them out and you can work whatever is in the top. So, x plus 5 is equal to 8. You set the powers equal to each other. Now let's solve for x. We need to solve for x. So let's move that 5 to the other side. And you end up with x is equal to 3. Now in exponential equations, you don't have to check your answers. This would always be true, because exponential equations don't have limitations like logs do. Now let's look at e to the power of x plus 3, and let's set it equal to e to the power of negative x plus 15. This is also an exponential equation, and we do have common bases. So when you have common bases, we're going to scratch them out, and you're going to end up with the powers. Okay, in this case, x plus 3 is equal to negative x plus 15. Now we do have an x in this side and an x in this side. So I'm going to bring this x to the other side. So I'm going to add it. So plus x. And x plus x is 2x plus 3. This goes away and you get 15. Now this is a nice linear equation. We do need to solve for x. So the first thing to go is not the 2, is the 3. So let's get rid of that 3. And you end up with 2x is equal to 12. Now how do you get rid of the 2? It is multiplied, so to do the opposite will be to divide by 2. And therefore x must be 6, because 2 over 2 turns into 1, and 12 over 2 turns into 6. And again, you don't have to check your answers, because exponential equations don't have limitations on their domain like logs do. Now let's look at a problem that has common bases, but we do have to use some of the properties for exponents. For example, when you multiply bases, if I condense this, when you multiply bases, the powers add up. So this is 6 to the power of x plus 3, and this stays 6 to the 10. Now we have a base equals a base, so they can cancel each other out, and you end up with x plus 3 equals to 10, minus 3 because I want to isolate the x. So I end up with x is equal to 7. Now this is also an exponential equation. We do have common bases. We just have to do a few operations. So condensing, for example, this is multiplication of bases. So it's e to the power of x plus 2. And 1 over e is the same thing as saying e to the power of negative 1. This cancels each other out, and you end up with x plus 2 is equal to negative 1. Isolate x, so minus 2 minus 2. X must be equal to negative 3. If I am going to condense this, things that multiply, they're positive, things in the bottom of the fraction are negative. So I'm going to write one base of 7, and it's going to be x plus 2 minus 5 equals, what is the equivalent to 1 over 7 squared? Well, that is equivalent to 7 to the power of negative 2, because the negative power represents a fraction. Let's combine these numbers right here. 7x minus 3 equals to x minus 2. Now we do have common bases now, so they cancel each other out, and you end up with x minus 3 equals to negative 2 plus 3 plus 3, x must be 1. Now we do have common bases. This is still multiplication right here, so we do need to condense it. Write 1 base of 11, and we're going to add the powers. So it's going to be x plus 3 plus x plus 2 equals to 11 to the 20. When you multiply like bases, the exponents add up. And in this case, this is 2x plus 5, and this is 11 to the 20. They go away, and you end up with 2x plus 5 equals to 20. Let's take away the 5, and you end up with 2x is equal to 15. This is multiplication, so we divide to get rid of the 2, and therefore x must be 15 over 2. Now what happens when you don't have common bases and you want to do it this method? Sometimes you can transform the 9 into the base of 3. So I know 9 is made out of 3 and 3. So in reality, 9 can be written as 3 squared. Then they do have common bases, so x must be 2. They don't look like they have common bases, although 27, we're going to do a factor tree. 27 is made out of 3 and 9. 3 is a prime, so we're going to leave it alone. But 9 is composite. That means we can break it even more, so that's 3 times 3. Now this is a prime, this is a prime. So the equivalent to this is 3 to the x plus 10 equals to 1 over 3 to the power of 3. And let's write that fraction in negative exponent format. So this will be 3 to the negative 3. Now you do have common bases, so you can cancel it out. And you end up with x plus 10 is equal to negative 3. To isolate the x, we're going to move the 10. And x must be negative 13. This one might be hard to tell that they do have common bases. A little clue is that I'm working with a base of 2, so maybe if I divide 2,401 by 7, it will work. So let's see, 2,401 divided by 7. It's telling me that 241 is 7 times 343. Now 7 is a prime number, so we're going to leave it alone. But what happens if I factor this by 7? So divide by 7, I get 7 times 49. Guess what? 7 is a prime. And 49 is made out of 7 and 7. Prime, prime. So in reality, this is 7 to the power of x plus 9 is equal to 1 over 7 to the 1, 2, 3, 4 to the 4. Now I do have to have common bases. This fraction is to be expressed in a negative exponent form. So I'm going to write it as x plus 9 equals to 7 to the power of negative 4 is the equivalent to that fraction. Now that we have common bases, this goes away, and you end up with x plus 9 equals to negative 14, negative 4. Minus 9 x is equal to negative 13. Equals to 1. It is not obvious that I can convert this into common bases, but we do need to remember a property that says anything to the power 0 is 1. So when you see a 1 and you want to have the base of 6, the only thing you have to do is say 6 to the power of x plus 9, and 1 can be written as x to the power of 0. So anything to the power 0 is 1. Now we do have common bases, and you end up with x plus 9 is equal to 0. Move the 9 to the other side, so minus 9 minus 9, you get x is equal to negative 9. So if you have a 1, it's most likely the same base you have over here to the power of 0. Well, 49, the base of 49 and the base of 7 are not the same. But I know if I factor 49, it's 7 squared. So in reality, I'm just going to write 7 squared to the power of 5x equals x 7 to the power of x plus 11. Now 2 is a power, 5x is a power, power to a power multiply the powers. So this is 7 to the power of 10x equals x plus 11. They do cancel out, and you end up with 10x equals to x plus 11. We do have x's in both sides of the equation, so let's move this x to the other side, and you end up with 9x equals to 11. Let's divide both sides by 9, and you end up with 11 divided by 9, which is 11 ninths. I know if we take 343 and I factor it by 7, is 7 times 49. 7 is a prime. And 49 is made out of 7 and 7. So the equivalent to 343 is 7 to the third power. And we're going to raise it to the power of 5x. We're going to divide it by 7 to the 8. Now, 1 needs to be the same base as 7. So the trick is to say 7 to the power of 0, because that is equivalent to 1. Now, this is a power, this is a power. Power to a power, multiply the powers, so that's 15x over 7 to the 8 equals to 7 to the 0, which is 7 to the 15x minus 8, because the 8 is in the bottom, it's going to divide, and it's going to be 7 to the 0. This cancels, and you're going to end up with 15x minus 8 is equal to 0. Move the negative 8 to the other side, so it becomes positive 8. Divide by 15, and you end up with 8 over 15.